Hey everyone. Right, if you're wondering where the 18th edition videos are, they're being made. There's a few of them. We're getting them together. Now, Joel commented on our last video and he was asking for us to contribute a video maybe to help him with his preparation for his 2392, which is the initial verification, inspection and testing course, level 2. So, I thought why not? So what we're going to do is fly through a trimmed down version of presentation. This isn't the presentation, this isn't the course, clearly, because it's a short time for videos and all that stuff. But what I'm going to do is highlight some key revision areas, explain the layout of the course, and hopefully some of this will be useful. And what I might do at the end, depending on the length, or add another video, is cover the mock assessment, so we can go through that as well. Okay. So with regards to the 2392, it's split into two separate units. One unit is obviously assessed with a theory test. This is your online multiple choice exam. The other unit will be assessed via practical assessment with an assessor. The theory is 50 questions, 100 minutes. It's a closed book. So a lot of the revision we're going to take from this will be from the guidance note 3 here. Which I do advise that you get, but it's going to be closed book in your assessment. Don't worry about that. Of the assessment you have there, many questions coming from the testing application side itself. I'll give you a good idea as to what kind of questions there will be. The practical is required for the candidate to carry out a full initial verification. This includes inspection, testing and the certification of an installation in the current version of the regulations. You'll be provided with the right installation. You'll be provided with all the documentation by your assessor, but you must carry out a safe and in sequence initial verification. You must complete the certification properly, and you must complete the schedule of inspections and the schedule of test results properly. I think it's like 2 hours for that. I could be wrong. So let's talk about some of the key criteria that's picked up, especially in the theory assessment. That'll be delivered on the course. The first thing that's always challenged is your knowledge of statutory versus non-statutory reference. What is non-statutory, what is statutory? This is covered in all the inspection testing courses really, so we know that there are legislations that say we must maintain, but the documents that we maintain or test to aren't necessarily the legislations themselves. So statutory documents, Health and Safety at Work Act, Electricity at Work regulations. What else have you got? You got PUA, Provision Use of Work Equipment regulations as well. Non-statutory documents, you've got BS 7671 on-site guidance notes, anything with the IET on it really. Okay, we're going to use both through this, and you need to make sure you identify what a statutory one is and a non-statutory. Something else you'll need to study is the information required before you carry out an inspection and test. The initial verification has to be done during and on completion, and so you'll need to have design information. This design information must be to the current standard. So access to design information will be of great benefit, so you can verify the design and you can calculate anticipated measurements. So you may have information that tells you what a conductor's size and length is, so you can verify that. Existing installations may have been installed per prior standards, therefore if we can have previous test information, we can then measure and compare to the previous information. Previous information is very, very critical if we're working on existing systems. Periodic inspection and testing isn't covered in the 2392, it's mainly on the initial verification. But it's important to know why periodic inspection testing is carried out, so you kind of know when to go on to that other area of work, and you may be challenged on that in the assessment. So the causes or the needs for periodic inspection testing, these are the common examples here: changing of an ownership, changing of use, occupancy of a building, licensing requirement of local authorities, insurance, property age, etc. What you mustn't ever put down on a periodic certificate is requested by the client. Periodic reports are never done because they were requested by the client. They're done for a purpose, and we need to make sure we know what that purpose was. Something else is absolutely paramount before you do an inspection and testing course. is you've got to have a knowledge of BS7671. Inspection and testing is done to BS7671. When you're inspecting, you're thinking of the content of that book throughout that process, and it's the book that you're comparing your observations to. The inspection testing course 2392, as well as the other ones, will pick at your knowledge of the regulations. So if you haven't got a sharpened up knowledge of the regs, it would be good to do a bit of reading on that as well. This is a good example question. It may come in a 2392 assessment, but this content will not be delivered in the course. This content is basically challenging your back knowledge. You're not going to cover this material in a testing course, but it will be picked up in your assessment. So make sure you've got a good understanding of the regs. If not, I'm not going to say do a course again. I'm going to say refresh your head on it. Here's another example of a question for volt drop. Same thing. Not covered in the syllabus. Trainer might mention it. It's picking at your knowledge of the regulations. Some of the things we need to consider. Supply characteristics. Have a good look either in Guidance Notes 3 or the wiring regulations themselves at the certification. Look at what the supply characteristics are and look at what we need to report. You'll be picked up on those so that so it knows what you're going to, so that the assessment knows that you know exactly what you're looking for straight away. So with supply characteristics, you've got maximum demand and diversity. Will the supply match the called for load? With regards to maximum demand and diversity, you've also got to consider thermal strains as well. Type and ratio of the overcurrent protective device, arrangement of live conductors, external earth full loop impedance, and the prospective fault current. These are all supply characteristics, and your knowledge of them is important. You may be asked which supply characteristic can be obtained by measurement. Well, that's clearly going to be either your ZE or your PFC. You're not going to measure an arrangement of live conductors, for example. You also need to be aware of the diagram requirement. So 514.9.1 tells you that you need to have labeling and a diagram that gives you the type and composition of a circuit, the equipment sensitive or vulnerable to typical tests, the method for compliance with 410.3.2, so ADS if that's your predictive measure. All that needs to be documented, and labeling needs to be applied with that information on it for future designers. Make sure it's there. Certification will be picked up a lot, but with this course we're only looking at the two. We've got the Electrical Installation Certificate, the EIC, and the Minor Electrical Installation Works Certificate, or the Minor Works Cert. The Electrical Installation Condition Report, or the Periodic Report, is shelved for this course, so your detailed knowledge of that report probably won't be a problem. With regards to the Electrical Installation Certificate, you've got to know on what occasion is that the needed document. So the Electrical Installation Certificate is needed for any new installation, any newly installed circuits, or if we're going to install a new consumer unit or actually replace an existing consumer unit. These are the situations where an Electrical Installation Certificate must be done. The other way, the Minor Works, this is where we're going to add to existing circuits, lighting or socket outlets, etc. So you must know which certificate for which type of work you will need. Also with these reports, we've got to consider who applies the signature on these documents. This gets challenged a lot. So there's a box for signing the design, the construction, and the inspection and testing. So quite often the one that's the wrong one, or the answer that's the wrong one, is the client or the person ordering the work. They do not sign on these documents, but what might be mentioned as well though is they are the ones who the documentation is actually issued to. So they're not issued to the designer or the site manager or the head contractor. They, all certification reporting must be issued to the person ordering the work. With regards to the inspection, it is essential that detailed inspection be carried out both during installation and immediately prior to testing. It's incorrect obviously to have a practice where one team does an install, then one team comes afterwards to do a test. The initial verification has to be carried out during the installation procedure, because there'll be inspections for different erection methods. There'll be certain methods of installation where once you've sealed it all up it can't be inspected again, or some inspections are just omitted because of the cost or the fabrication, or maybe the higher equipment or plant has been removed from site. This must be carrying out as the installation progresses, and then another one before we energize the system. Duty holder. This is quite often picked up in the assessment. Is it a job title? Is it a role? Is it responsibility? As far as the guidance of the electricity at work regulations is concerned, a person who has responsibility for the system is this duty holder. But it's not a job title. You can't necessarily say, oh yeah, you're the duty holder, you're the duty holder. It's a role in law. It's something that is inherent according to the nature of the work. So it's important to understand that the person responsible for the equipment and the work being done will be the duty holder. Now, if you are the principal duty holder, you may be in charge of the overall site, but then you'll have persons in charge of their own little work areas who will be themselves duty holders. Okay, so it's a role, it's a title in law, not a job role. Another common thing that will be picked up will be sensors. Now, so when you're doing inspections, which sensors will you use for which kind of event? So if you have a damaged cable or a burnt out cable, you're likely to smell that or see that before you actually touch that. So we have sight, sound and smell, and we try to avoid touch as much as possible. So have a good think about what kind of things can you find on an inspection, and which is the best human sense to utilize to actually inspect that accurately and to find it safely. It'll also be worth, I'll put a link in the video to download GS38 if you haven't seen or heard of it before. It'll be referred to by your assessor and also through the training course. Any test instruments that we use for the isolation procedure and actually doing the installation tests must comply with the requirements of GS38. And to summarize them briefly, this is to ensure that the finger barriers are in place, that we cannot obviously slide our fingers down into live parts when we're applying some pressure. To make sure that the tips that are exposed are 4 mm, preferably 2 mm of exposed metal parts, to make sure we don't have any shorting out when we're in small control panels. To make sure that there's a fused lead or a high capacity resistor in the lead so that we don't have any arcs or anything when we're holding the equipment, and just to make sure it's overall in satisfactory condition. But it's free information, so do make sure that you get it and just update yourself on that so you haven't got to relearn it when you're on a course. It's best to learn as much as you can ahead, so that when you're on there you're just kind of, yep, I've got that, and you're kind of taking useful information in instead of stuff that should be free information that you can learn easily. You'll cover the isolation procedure. Now, this is just an illustration that is quite common. Your assessor may have a certain way of doing it, but make sure that the safe isolation procedure is understood by yourselves, but also make sure the assessor, who will be observing you doing the practical, is understanding your procedure, or use his procedure. Because if you use your own procedure that is slightly deviated, he'll question it and he'll flag it, and you don't want that. All right. But main principle here is we're gonna plan the work. We're going to unplug any equipment, isolate it, etc. Here's the key part here. Grab your previously inspected voltage indicator. I should have mine in my hands. I don't know where they are. They'll be on my desk somewhere. And we're going to prove them in a proving unit. This is this box thing here. And then we're going to go to the point of isolation, and we're going to prove isolation by going on the live conductors and the earth and the neutral. And there is a sequence. Yeah, so you go on the line last to come off the line first. You'll hear all that as you go through it. And once you've verified that they are isolated, you're then going to come off. So you've proved, you tested, and you're then going to prove again. There are many resources on the isolation procedure, so this shouldn't be new, really. But yeah, prove, test, prove, lock it, sign it. I'm probably going to create a video on it later on if people ask for it, but there should be many online resources for the isolation procedure. It shouldn't be an issue. If you've got any of these neon screwdrivers, throw them in the bin now. They shouldn't be in the training, they shouldn't be in the industry. They're a piece of crap. Alright. If you've got, again, where's mine? Oh, it's down there. If you've got an all-in-one multi-function tester like a Mega or a Fluke, you've got to break that down. That instrument isn't a Mega or a Fluke. It's a clever piece of kit, but it's a low resistance ohmmeter. It's an insulation resistance tester. It's an earth fall loop impedance tester. It's an earth electrode tester, or it might not be, depends on how much money you spent on it. and it might be an RCD tester as well. Okay, you need to remember the individual titles of those instruments, because if you're asked what tester would you use for this test, you don't say I'll use my Megamate. You say, oh, I will use the low resistance ohmmeter, and then that's something you need to remember. Okay, so get used to those terms. These are all given in Guidance Notes 3. So the low resistance ohmmeter, continuity tester. This is key information here. It must read a scale as low as 0.05 ohms. This is so you can verify bonding continuity, for example. And the voltage it applies is between 4 to 24 volts DC on the battery, with a current of no less than 200 milliamps, so you can apply a good continuity measurement. What's important though is to understand the units that are given by these instruments. So the continuity tester, or the low resistance ohm meter, measures in the ohm or the kilo ohm range. It doesn't measure in the amps, and it doesn't measure in the mega ohms, and it will need to be nulled due to the low accuracy that it measures to. It's used for continuity of protective conductors and continuity of ring final circuit tests. And with this illustration here, it's the orange section. Yeah, it's the orange section there. So you set to ohms. The red section is your insulation resistance section. Still an ohm meter, but this reads in the higher range. So the instrument changes to a little DC generator here, offering voltages of anywhere up to 1000 volts. I think this illustration here is 1 kilovolt. It's set on 1 kilovolt. We normally would use it on 500. I don't know why that's on 1 kilovolt. But the insulation resistance tester has a number of voltages, and it measures resistances in the mega ohm, which is the large M. Never write it down as a little m, that's the milli. Get your millis and your megas straightened out now. Sort that out now. Other test instrument, the earth fault loop impedance tester. We'll use this for verifying the supply earth at the origin. The ZE will measure the earth fault loop impedance at points through the system, at sub-distribution boards, and at every point of utilization of a circuit. So the ZS. We can also use it, you'll see this picture here, there's a PFC button on it. So we press that button and it just does a bit of Ohm's law, changes the ohms to amps. Okay, so we can also use it for measuring the respective earth fault current and the respective short circuit current. In the case of earth fault loop impedances, these are given in the ohms scale. If we switch it though to the Ka or the A, that's the amps, that is the fault current scale. So get an understanding on resistances is your ohm and currents is your amps. Get an understanding on the different test readings and test scales, because they could be picked up quite easily in any assessment that you have. You've got your earth electrode resistance tester. Now, probably not going to be much content on this in this 2392. The 239 4s or 5s, or the new 23915 suite is probably where this would be more divulged, but we have two methods of doing earth electrode testing. We have the dedicated earth electrode resistance tester, which is there's a few types. There's 4-stage, 3-stage. There's also a stakeless type. Or we can actually, for testing electrodes, use an earth fault loop impedance tester if it's a TT system with an RCD on a live supply. Okay, but again, it's just like another method of using high reading ohm meter. So it's like an insulation. Some people might call it an earth mega. It's like a DC generator applying a voltage into the ground. The difference with the electrode resistance tester is you need the more ports for the more probes to actually get the reading through the soil. So it's a slight adjustment to the normal insulation resistance test there. We have the RCD tester. Must be able to test at times half, times 1, and times 5 for ADS purposes. Some RCD testers will have a ramp function, which isn't a requirement, but it's quite a useful diagnostic tool for nuisance tripping. It's important with this test though to verify the earth fault loop impedance first, as the RCD test must not rise above 50 volts AC RMS at any time, which is why the test is only carried out for a fraction of a second, because we can't allow dangerous voltages to build up if there's ineffective earthing in the area. Something that will be mentioned a lot is checking your instruments. So Instruments require regular testing and calibration. They should have a current test certificate. Normal time span is a year. That's kind of like it's an unofficial rule. What you need to do is ensure the equipment is fit for use, it's used properly, stored properly, and it's appropriate for the nature of the work that it's going to be doing. So the two ways we can often do this, we can do regular checking with instruments using resistors or check boxes or pre-check boxes, or we can annually calibrate it. Again, an annual calibration is kind of a tick box exercise. What you really should be doing is considering the dependency on every instrument and deciding if that's enough. It most likely, if you get it out now and then, probably would be okay, but I'd always self-check it before I used it on something that I know a value of as a self-checking activity. The tests. There are lots of them. This is the full sequence of tests. Continuity of protective conductors, including main earthing and supplementary bonding. Continuity of ring final circuits. Insulation resistance. Protection by self, PELV or electrical separation. Protection by FELV. Protection by barriers or enclosures provided during erection. Insulation resistance of non-conducting floors and walls. Polarity and earth electrode resistance. That top half are all tests carried out on a system before it is energized. Don't confuse that with live work, dead work. Okay, the system is on or off. The work itself is still, in some cases, live. For example, insulation resistance testing is live work. Yeah, dead system, but live work. That little list there, you're not going to have to remember them off the top of your head, really. If you could, that'd be great. But when you do your assessment, you'll have to carry them out in sequence, but you'll only be carrying out a few of these. You'll be carrying out continuity of protective conductors, continuity of ring, insulation resistance. That's it. Then you'll go down, polarity. Self, PELV, FELV are if they are part of a system. Yeah, barriers during erection, again, if it's required during the erection of a system, they're not going to be part of your assessment. The live system tests are fault loop, additional protection with RCDs, prospective short circuit current, checking of phase sequences, functional testing and voltage drop. Again, you'll do the earth fault loop test. You'll then probably do the loop test and the prospective fault current near enough at the same time. That's what I do. But then you'll do the RCD tests, and then you do your functional. So whilst the list is long, hopefully your assessor will introduce you to the assessment. You'll go, oh no, we're just going to do these 7 or 8, whatever it is. Okay, but the ones that you do, you must do in this sequence. Something that you may understand it, you may not understand it, but something you need to become familiar with are the conductor terms that we use in testing or design, simple design. So we have R1, Rn, R2, little r1, little rn, little r2, R1, R2, R1, Rn. If you don't understand straight away what they are, then you're just going to get a bit confused with all this. So the upper and lower case is important. So R1, Rn, R2, these are the measurements of a cable. So a line is R1, a neutral is Rn, a protective conductor or an earth is R2. If I'm on a ring final circuit and I've taken the board off, I've got my line going off, I've got my line coming back, that returning cable, whilst it's the same kind of test, that is known as a little r1, so it's a returning measurement. And then I have little rn for the returning neutral and the little r2 for the returning CPC. The R1 plus R2 is a measurement of the line conductor, and maybe at the end it's been connected to the earth and the earth conductor back. So I'll connect the line and earth at one end, or the line and protective conductor at one end, and I'll measure across the other two at the other end to get a measurement of that circuit. R1 plus Rn, same thing, I've just connected line to neutral instead of line to the protective conductor. You'll see them used in a few tests' time. ZE and ZS, these are, again, R is resistance, which is done on a de-energized circuit. Z is impedance, which is a measurement of resistance, but on an energized circuit. So they're both resistive measurements. They're both measured in ohms. It's just one is resistance and one is impedance. Okay, so the ZE is the external earth fault loop impedance. So this is the resistance pathway that is supplying your installation. So your take away your system, you won't have any of that connected. You'll take the earth out to remove the parallel, and you'll go from line to earth, and you'll get a measurement of that supply loop. If it's good, you'll use it. If it's not good, you'll keep your system de-energized and you'll wave to the supplier to fix it. And they'll probably tell you to put your spike in and make it a TT. The ZS is the supply loop of ZE plus the internal loop of your circuit of R1 plus R2. So you may have heard that formula before. The ZS is equal to the ZE plus the R1 plus R2. The total loop is the overall value of the external plus the internal loop. Okay, you'll see these units popping up a few times in all testing inspection courses. It's one of the building blocks of these courses, really. It's your knowledge on units. Alright, so with continuity testing, start at the basic tests here. All protective and bonding conductors, or conductors, must be tested for continuity to ensure they are electrically safe and correctly connected. Yeah. The test is called continuity of protective conductor, and what you need to remember is, if I install a circuit and I put something at the end of it and I turn it on, if the thing works, then it's likely that neutral and line have got there and they're doing their job. You don't know if the protective conductor or the earth is actually there, because if the thing has no earth, let's say it's equipment like a shower or something, if the earth hasn't got there, the absence of an earth isn't going to make that stop working. It's just going to carry on working. So you've got no idea. So we have to actually physically take our time and actually say, right, we'll test from this supply earth to this end earth to make sure it's there. Before we do that, we've got to select the instrument. We've got to make sure that it's got sufficient battery power, and because again we're measuring accuracies that are quite low in resistance, we'll have to zero the leads or null the leads as well. So we need to remember as well with continuity testing is the parallel. Now if I have a piece of equipment that has, let's say I have my connection in the board and there's a connection to the water pipe, and that water pipe goes to the shower, and for some reason there's a cable from the pipe into the earth on the shower. I don't know why, but that's what's illustrated here. Yeah. If I then test the continuity of the earth from the board to the shower and that is broken, the parallel back would give me a false reading. So I must always do these tests and disconnect parallel paths as best you can. Always be aware of parallels. They're a nightmare. Yeah. In twin and earth insulated systems, they're quite easy to control. In larger complex systems with metal conduits, metal trays, and you find yourself getting low readings to earth, it's likely that the parallels are having an effect, but you need to be able to take account for that instead of just going, must be a parallel. You make sure you understand why they're there. Two methods of measuring continuity. Method 1, this is an R1 plus R2 test. Method 1 has R1. That's the good way of measuring it. So here, we're going to ensure the equipment is dead. We're going to prove it's dead. And what we're going to do is disconnect this illustration is a bit rubbish really, but we're going to disconnect all the parallels of the circuit. So here they've disconnected the bonding to free up the earth on the bar. I would say disconnect the earth from the bar. That's what I'd do. Alright, take the circuit's line, take the circuit's earth, put them together, either in the breaker or in a connector, or I use the Wago flex lever things. They're together, okay? Then go to the final point of the circuit and measure between them. Now if you have continuity of your protective conductor, then you'll get a reading. If it's broken anyway, you'll get no reading. And that's it. That's method 1. We're using the line as a return path to make testing simple. We link it at one end, we test it at this end. Good job. But the point of the test is to verify the earth is continuous. So alternatively to method 1, we could also use method 2. Method 2 is just testing R2. So we haven't got a return line, so what we use as instead is a wander lead. So, because our test leads are only so long, meter or two, So we'll zero out this test lead, plus we'll zero out this long wander lead, which could be anything up to an ohm. And then we'll run the wander lead out from the board, crocked onto the disconnected earth, and at the other end we'll just test from the port on the wander lead to the exposed conductive part, or whatever the earth is that we're testing to. Okay? It's a very effective way of testing light switch drops or metal containment. It's the only way you can verify bonding, because there is no line conductor to bonding. The problems with it is it does create a bit of a working difficulty with safe working because of the trip hazard. But it's a good way to fly around and collect information quickly if you can control the work safely. What you need to know though is what the reading should be. If I'm going to go to a socket and go, there's a number, is that number any good? Do I know what it should be? If it's an initial verification, I should have some designer information. Might tell me what the measurement should be, and I'll go, great. If I haven't, I might need to collect some other information and understand how to calculate it myself. I also need to be aware of other effects on resistance, like increasing in length. So if I have a reading that is higher than the designer has said, it might be that the cable's length has increased. Maybe it was run in a different way. Or it might be that the cable that was selected was smaller than the designer. So an increase in length will increase in resistance, an increase in temperature will increase in resistance, but an increase in size will decrease resistance. So a decrease in size will increase resistance. Think about that for a minute. Alright, this is a picture from a table in your on-site guide. This table is also in Guidance Notes 3, and it's also, I think, in the PAT testing code of practice. If you're going to do a test for R1, R2 on a cable, you need to know its length. Hopefully the drawings will help you with that. You need to know its size. You can then decide whether to accept the number. It doesn't take an idiot to press a button and for a number to appear. The genius is being able to go, that number's no good, that number's not right, and then working with that. So let's say we've installed a 2.5 mil 1.5 mil twin and earth, 27 meters in length for a radial circuit, and we're going to test at 20 degrees, so it's a de-energized circuit. This is the table from the on-site guide, and it tells you that the 2.5 mil 1.5 mil combined resistance is 19.51 milliohms per meter. I multiply that by the length of 27 meters to give me 526.77 milliohms. I don't want milliohms, I want ohms. So I divide by 1,000 to get 0.53 ohms. If I've measured 0.51, 0.54, 0.56, I'm happy. If I've measured 0.84, I'm like, don't like that. Okay? So make sure you can interpret information. You will, in your assessment, you won't be given obviously much because you won't have this book in front of you, but what they will do is give you a resistivity such as 19.51, and they may ask you to calculate its length, or they may say to you, okay, well this was the resistivity and this is the length, so what should its resistance be? So there will be a little bit of math needed for this area of the course. Common problems with continuity, we've mentioned the parallels. Other things that could be a problem is when we go through light switches. So if I'm measuring at the switch line and I've gone through the switch to get to the switch line, if I'm buying my light switches from some bucket in a car boot sale or something, or probably the latest MK ones, I'm going to have some high contact resistance. So it might be that the switch is naff, but they can actually start spiking up your resistance value. Sometimes a good couple of switches might help. It might be that you've recognized a faulty accessory and you've got to bin it. I don't know. But sometimes if you have spiking measurements, it might be a connection or a switch that's created the problem. It might not be conductor length or size. Continuity of ring final circuits. Remember, I'm pushing fast through this. This is in no way how quick you should be learning it on a course. It should be a lot slower. Time to digest all this and have a go at it. With the ring final though, we're still going to use the low resistance ohmmeter. It will have to be zeroed. The difference here is we've got to make sure that there are no internal loops and that the ring is in itself a ring. If the ring isn't a ring, then we're going to have potential overload because we've got a 2.5mm cable on a 32 amp breaker. That's no good. So a true ring final circuit will have 2 lines, 2 neutrals and 2 CPCs. So this is like a spur-free ring final. There are 3 steps. Remember that, might be a question. There are 3 steps to the ring final circuit. The end-to-end measurement, the R1 plus Rn measurement, and the R1 plus R2 measurement. So the first step, the end-to-end measurement. This is to verify your ring is a ring. So I'll go line to line at the board. If my line to line gives me open circuit, I know at one of these sockets the line has come out and I've got to fix that. I'll go line to line, get a reading. I'll go neutral to neutral, get a reading. I'll go earth to earth, I'll get a reading. And we record those in the lower case, little r1, little rn, little r2. If you look in the schedule of test results, you'll see there's a dedicated box for those. If it's a 2.5, 1.5, then the line and the neutral should be the same because it's the same size. The smaller earth size would result in an increase in resistance, and we have that ratio of 2.5 over 1.5. 1.67 is the multiplier to get from one to the other. We can also calculate step 2 and 3 though once we've done this. So in this illustration here we've got a little r1 or a line to line of 0.54, little rn or a neutral to neutral of 0.53, and a little r2 or a CPC to CPC of 0.86. That's fine, great. Step 2, the R1 plus Rn, we can calculate that because it should equal the line to line value and the neutral to neutral value together divided by 4. Okay, and step 3, we can calculate the line to earth the same way. Now your assessor should give you a lot more time to understand why that is, but to briefly cover it, we want to make sure there are no internal loops. So we measure the end of one line returning to the other. But then to make sure there are no internal loops, we're going to cross connect them. So we're going to take the line of that leg with the neutral of this leg and vice versa. And this creates what we call the figure of 8. So the line going out that way connects to the neutral coming back, the neutral going that way connects to the line coming back, and it's out of the board, so it's like a floating figure of 8 in the system. We're then going to go around the system and measure from line to neutral, or line to earth, depending on which test we're doing here, at each socket. So when we do that, the first reading we had, which was line plus neutral, the reason we've divided by 4 is when we go around going from line to neutral each socket, the pathway of that measurement has halved, because it's no longer this loop of line plus this loop of neutral, it's just this half loop of line and neutral. So the length has halved. We're also going from one conductor in each terminal or each connection of line to line or neutral to neutral to 2, because there are 2 neutrals and there are 2 lines in each terminal. So the length has halved, halving the resistance, and the cable size of the measurement has doubled because there are now 2 cables under the test probe. So if the cable size doubles, that halves the resistance. If the cable length halves, that halves the resistance. So if you halve the resistance twice, we quarter the resistance, and that is where the formula of little r1 plus little rn over 4 comes from, or little r1 plus little r2 over 4. Take some time to understand that, Google it, or just listen to the tutor when he explains it. It's not absolutely paramount that you understand it bang on. What's important is that you understand the math for now. Okay. If people want to ask in comments and stuff, I can have a longer winded effort at drawing it out and understanding it better. Right now I can't be asked, basically, because it's a bit of a mouthful. Okay, and here's the R1 plus R2 version. So R1 plus Rn was 0.54 plus 0.53 over 4.26. Just recognize the math. This is the math that you'll be covering. And then here, R1 plus R2, 0.54 plus 0.86, because little r2 was of increased resistance over 4.35. Okay, we're going to leave that there. Once we've got those, though, we need to then understand what we can decide with those. So, this little table, for example, A ring final circuit gives the following results. You have an R1 plus R2 of 0.52 and an R1 plus Rn of 0.4. Makes sense. This means that every socket outlet, the measured value should be 0.05 of either side of 0.52 ohms when testing from line to earth, R1, R2, and it should be 0.05 either side of 0.4 when testing between line and neutral, R1 and Rn. 0.05 is our tolerance for connection resistances. If we go beyond that tolerance, then we're basically going into guess knows country. We don't know where we're going. So we stay within 0.05 tolerance up and down. So we've got here sockets A, B, C, D, E, F and G. Socket A, the line to earth test 0.52, the line to neutral test 0.4, bang on with the top readings. So it's a good reading. With socket B, we had 0.48, which is within 0.05 tolerance of 0.52. That's fine. We had no reading from line to neutral. Now if I have a measurement between line and earth, and I have no measurement between line and neutral, it could be that line and earth, while I had a measurement there, in the socket outlet may have been swapped around. Because to have nothing between line and neutral, but something between line and earth, suggests that line and earth are the wrong way around. Okay. Socket C, 0.55, 0.44, a good reading. Socket D, no reading for line to earth, and now a good reading from line to neutral. So no reading there, but good reading. Well, that's the opposite to B. So it's probably now that we have a line and neutral reverse. Okay. I can go through this slow if you want comments on this. Just say it. Just mention in the comments and I'll go through it more. E, got a slight increase in resistance here. This doesn't mean a loose connection or a disconnected socket, because if I had a loose connection, then my first test, my end-to-ends, wouldn't have been there. It's likely to be either a twisted pair that has become slack, or a high resistance through the plug, if I've measured through the plug, or it could even be that this socket's a spur, so there's an increased resistance in that cable supplying this socket outlet. F and G are just good readings, so they're fine. I have handouts that kind of cover this table and stuff. If you feel you need some more support with this, so let me know. The installation resistance test. This is the electrician's pressure test. The important part with this test is preparation. So we need to remove all equipment, remove all loads, remove all pilot indicators and stuff. I mean, to be honest, with initial verification, you should probably do this test before you insert them. Really. Disconnect all loads and have all earthing connected. Now there are a couple of ways you can do this. Now if you're working on a single phase board, this is the way it's illustrated here. Main switch on, circuit breakers on, all of them, equipment out, and they've connected to the supply tails coming in. Now if your supply tails are going into a service head or a meter, then you're not going to be able to do that. So the thing that you do differently is your main switch would be off, and you'll go to the supply side, the load side of the main switch, the isolated side of the main switch. You'll go there instead. Okay, so if you can't take the tails out, fine. Main switch off, locked off, and test on the load side, the dead side of the main switch. But the MCBs and breakers must all be in the on position. If they're in the off, then you're going to get a good reading because you're testing absolutely nothing. Alright, so you must be testing something. The two tests that are required illustrated here is between live conductors, so line to neutral, and between live conductors and earth. So what they're saying here is, oh, if you do it this way, you can just go in one test from line and neutral together to earth. Sometimes it's just quicker to go line 1 to earth, neutral to earth, line 1 to neutral. Sometimes it's easier to do 3 tests than set it all up to carry out 2 tests. Alright, see, with regards to the way you're going to do it, there could be 100 different ways, really, but see which way the assessment rig is set up. The assessment rig might be set up to encourage one way over another. Other thing with installation resistance testing is your two-way switching, any intermediate switching. When we do a test to line and earth, and neutral if there's a neutral in the switches, we need to do it once, and then switch one switch to switch over to the other strapper, and then we need to repeat the test. Otherwise that line of conductor that wasn't in circuit hasn't been tested. the installation resistance test, giving you a value of the total installation. It's a combination of all individual resistance values of all circuits, and they are connected in parallel with each other. So when I test a fuse board, I'm testing the parallels of all the circuits that are on that board. Okay. If my reading is low, I can then break it down to test the circuits individually. But that's what I need to understand, is that my resistance overall is the combined parallels of the system. And the wiring regulations basically says that all final circuits can be prepared to a single consumer unit. If you've got two consumer units, then you do the test twice, one for that board and one for that board, for all of its final circuits. Here's an illustration of the math. So I'm testing circuits individually, and I've got 250 mega ohm, 100 mega ohm, 6 mega ohm, and 59 mega ohm. Now the formula, 1 over RT is 1 over R1 plus 1 over R2 plus 1 over R3, etc. This kind of math probably will be more in the 239455 and 239152 suite kind of course, but you do need to know about the rules of installation testing, and that's illustrated here with this formula. When I use the formula, you'll notice that the lowest resistance of the single circuits measured is 6. When I then combine them all together for a single measurement, by doing the math here, 1 over RT, the overall resistance value now has come below 6. So the overall value of insulation resistance is always lower than the lowest single circuit value. Right? So if one of these single circuits measured 2, I know my overall value will be below 2. That is important to remember, because in the assessment it might be that they'll give you, what are the rules, and the answer is lower than the lowest. Or it might be it gives you 4 measurements of insulation resistance, and it wants you to do the math. Remember, if it's a multiple choice assessment, just select the answer that's lower than any of the given measurements. Okay, the overall value in parallel will always be lower than the lowest single measured value. Okay, pushing on to your earthing systems. You've got your TNS system. Why is that grey? I don't know. Your TNS system. Understand the difference with your TNS system, your separate earth supply, to your TNCS system and your TT system. Have a good read on them. Understand how they differ. With that in mind, you need to understand earth full loop impedance and how the earth full loop impedance path works. So with regards to measuring earth full loop impedance, at the board, depends on if our instrument's 2 lead or 3 lead. If our instrument's 2 lead, we just go, as you can see there on the left, between line and earth. The important thing here is, if this is a ZE measurement, the parallels, you can see there the bonding has been disconnected, the main earth comes out and we go on the main earth, so we don't measure any earth that's brought in through parallel routes, through bonding, through water pipe work or anything. We only test the supplier that the provider has given us. So disconnect the main earth and go on that, or, as they've done here, take all the bonding and circuits out and go on the bar with just the main earth in it. If it's a 3 lead instrument, then you just add the neutral to the neutral, and that also will be a polarity indication, a live polarity indication, because this will be an energized test. This will be the very first energized test that you do, verifying the earth is there and it's good. Once you've done that, you could go off and do the final circuits. I myself would go on to do the PEFC and PSCC, because I'm at the board. I've got the board cover off, but I must, as you'll see here, difference between that one and that one, the parallels have gone back in. The bonding has gone back in. The circuit protective conductors have gone back in. So you're going to do the measurement again and switch it from the loop reading to the PFC reading. You must retake the reading. If you do this reading here and you get ohms and you then press the button that gives you PFC, you can't use that because you have to retake the measurement with the parallels in. It's likely that those parallels will offer a lowered resistance, which, thinking of Ohm's law, would result in a higher current, and you need to find out what the highest prospective fault current is. So we need to have all parallels reintroduced when we do this test. Alright. 2 lead, we have between line and neutral, that's the prospective short circuit current, and from line to earth, which is the prospective earth fault current. We measure both. As you can see here, 0.651 between line to neutral, 0.516 between line to earth, and they are in kA, so that's half a kiloamp. In this case, the reading would be the prospective short circuit current of 0.65 kA will become the PFC of 0.65 kA. We just take the highest as the PFC. If you have 3 leads, it can be a bit confusing. The earth measurement isn't as bad if you look on the right. Yeah, all we've done between this one and this one is taken that 3rd lead and put it on neutral. Another polarity thing. That's fine. Great. Look at the left though. When we do the prospective short circuit current between line and neutral, we don't want to go on an earth because that's an alternative resistive path. It's going to be a lowered resistive path. It's going to give us an inaccurate reading. So we double that up. That can be a bit awkward depending on your test lead configuration. You may have a piggyback system. You may be trying to crock one lead to the other. Discuss it with your assessor if it's a 3 lead instrument you're being told to use. I always introduce different instruments. I bring an array of them, and I always make sure that anyone who's brought their own has an effective rig to test safely, because it's important that you test safely. But you do, with the 3 lead, have to put both the neutral and earth for PSCC, the left one here, on neutral. Okay. The alternative to measurement is calculation, because we can, but we shouldn't. If you've already measured earth fault loop impedance, then the prospective earth fault current can be calculated using Ohm's law. The earth fault current can be calculated using I equals UO over ZE. That's Ohm's law. Yes and no. Yes, because textbook says yes. Yes, because supply information says yes. No, because ZE was parallel free. Parallel free is a good reading for ZE, a bad reading for fault current. Fault current with parallels could equal higher values. And if you mistakenly go with calculating from ZE, then you may end up saying, oh, that's fine, it's 8.7 kA, the 10 kA devices are fine, but when the parallel circuits are introduced, it could go up above 10 kA. That's no good. Alright, so what you need to do is understand the difference between measurement and calculation. Calculation is crap. Okay, the RCD test. Alright. What you need to understand with RCD testing is done at times half, times 1 and times 5 for every device. So you set the device to the rating of your RCD, 30 or 100. But you do half, you do 1. Understand the maximum times. If it's a 4293 or a 61008 or a 61009, those are all in your on-site guide. Those are all in Guidance Notes 3, 300 milliseconds, 200 milliseconds, etc. You should know those. 300 milliseconds is going to be your 61008, 61009 at times 1. Times half should be no trip. Times 5 is only if you're actually testing an RCD that's been installed for the purpose of additional protection. So if the RCD there hasn't been installed for additional protection, you don't times 5 test it. So people can be confused with that. Okay, but if you are times 5 testing it, then we know that 415.1 says 40 milliseconds, so it should be disconnecting within 0.04 of a second. Okay, fairly easy to do. Make sure you do it before you do the functional. Okay, and if your tester has the ramp function, might be a good idea afterwards to see if it's nuisance tripping or if it's very close to the lower limit, but it's not really essential. Okay. It's important to do this after the earth fault loop impedance tests though, because obviously you can have a built up voltage on the surrounding earth parts if there's no good earth. We also have verification of volt drop. It's a test. With initial verifications though, it's not a test. What it is verification that the designer's information is right. So the designer has designed a system with this cable, this route, this system, this method, blah blah blah, and you go, Yep, that's right. Then volt drop's already accounted for, so it shouldn't need to be done. If you do need to do it, then there is a method of measurement using R1 plus Rn and 1.2 and all that stuff. And, I can give information on that, but that's outside of the scope of this course, and I don't want to overdo it. Okay, and the last thing you're going to check is the functionality. So once you've got the rig and you've done all this, you've done your RCDs, you're then going to trip out your RCDs. You can go main switch, MCBs, anything else that's there that's an operational, functional operating device. Do it, because you need to know it works before you actually then say yes, that's free to use, go on and use it. Alright, where are we for time? 55 minutes, holy crap. Okay, I'm gonna stop this video. This is just a run through of the 2392. What I will do is another video with it that will cover an example of questions, which I'll upload pretty much with it at the same time. Okay, I'm going to go grab a cup of tea or something, but I will be producing some 18th edition videos talking about the public draft and stuff soon when I get some time. Any other questions, any other videos, guys, let me know. Ask questions on Twitter, Sparky_Ninja. Follow, share, whatever you want to do. Let me know what you want, or I can help you with, and I'll do my best. Bye bye.